Okay, so a principal role that an engineering geologist plays in looking at and assessing a piece of property is to conduct a thorough investigation. Geologically speaking, looking at the soils, the bedrock conditions for whatever structure is proposed to be constructed on the property. So you're looking at a view of the beachside cliffs at Torrey Pines Beach. Quite a striking picture, cliffs of 100 feet plus, and you're looking at various types of bedrock here. This is the Eocene age Torrey Pines sandstone. Up above it is the more recent poralic sandstone deposits. So the Torrey Pines sandstone is Eocene, and the poralics are Pleistocene in age. So you want to come up with a geologic model for each property you're investigating, whether it's founded on shallow bedrock or deep bedrock, deep soft soils, high groundwater, expansive clays, whatever conditions are present and existing which will affect the construction and design of the project must be assessed, must be characterized, must be identified. So we want to have a total approach for site investigation of a given property, an understanding of the full geologic history of the property, the distribution and the nature of the materials, anything of high significance, as I've mentioned before, such as possibly expansive thick clays or soft, loose, saturated sediments, high significance characteristics that you must account for. History of land alteration. Was there any previous grading done on this piece of land? Were there cuts made? Were there fills made? These are critically important in assessing a property. Hydrogeologic conditions, of course, the presence and the depth of groundwater. Seismicity. As you know, in California, we have high seismicity due to the nature of California's location on the continental borderlands. So we're influenced by seismic activity from the San Andreas faults, San Jacinto faults, and locally in San Diego, the Rose Canyon faults. They are all comprised of active strands or segments of faulting which can affect a project. So it's important to recognize where they are, assess their distance, their potential for large earthquakes. Ground conditions, of course, are vital in assessing the nature of destruction from any given large earthquake. If you're sitting on soft, saturated sands, you're going to suffer more damage than if you're sitting on hard, tough, dense bedrock. Tools. You need tools before you start the investigation is what I'm talking about. So you want to research any existing literature and maps that are available for the property, any photos, whether they're overhead aerial photos or oblique photos, and old investigation reports for the property or adjacent properties. It's very useful to have this kind of information. You may not always get it, but it's nice to have. So here's an example of a local condition in San Diego which really wasn't very well known or understood before, I think, the 1980s. This whole outlined area that you see here, outlined in heavy dark black border, is an area that's underlain at the surface and to a depth of 13 to 15 feet below ground surface of a very stiff, expansive, gray, bluish, brown clay, plastic clay, That's called, locally called the Normal Heights clay or Normal Heights mudstone. So it represents an environment of quiet water deposition of very fine soils over a long period of time, sitting on top of somewhat older formational sandstones, conglomerates, and mudstones. So this is important to recognize locally because it affects foundations and it affects potential grading and construction of a project. When you have something that's this unusual in nature, it's going to affect whatever you put on it. So here's a look at the actual material. This is the Normal Heights mudstone. You see it's very thick and gooey clay material, which is not very good for building on. If you build on it without doing some modification or getting rid of it or mixing it with lime or other soils, you're going to get an expansive clay underneath your structure. Add water to that expansive clay and the clay will swell and possibly crack or otherwise disrupt your foundation or the structure that's on it. So this is that thick clay that's sitting on top of the what we call varial parallex, which are nearshore shallow marine and beach sandstones and conglomerates. Okay, so it's important for the engineering geologist to investigate this, to be aware of it, to bring it to the attention of the design engineers and work with them in coming up with mitigation solutions for any particular structure to be built on top of it. Some other variable conditions, this generalized picture that I'm showing you here, in volcanic areas or areas with volcanic lava flows, often in between individual flows you have what's called an interflow lava breccia, which is sort of a crush zone. So you have one flow down here, which is older than the one above, but the one above runs over the top of it, and as it does so, it's heating up this zone. It's crunching and grinding and crushing stuff in between the two flows, this older cool down flow and this upper warmer or hotter flow. So you get a sort of a horizon that's composed of glassy particles which turn to clay-rich soils, crushed material. Sometimes you have a zone of gas bubbles permeating these types of breccias. So it's another example of a foundation material that you need to be aware of as an engineering geologist. Here's a close-up of that breccia. Here's another look at it. Down here you can see, might be hard to read, you have one flow up here, you have one flow here, you have another flow here, and you have red soil mantle, which is a soil that's developed on top of this older flow as a distinct paleo soil, we call it. Or here's another example of the different types of layering you might find in a stack of several flows. A completely different kind of condition which engineering geologists have to deal with, not too often in California and not often at all in San Diego area, karst. Karst is a type of landscape that's formed within limestone bedrock primarily. Limestone is prone or susceptible to dissolution by acidic groundwater and rainfall. So that can result in a underground or subsurface that's full of voids, where you might have these voids fill up with soil. You have formation of what's called a sinkhole. And as some of you know from news reports you may have read, sinkholes are a dangerous and unsuitable construction condition. If you build a house on top of a sinkhole, which is infilled with soil, if the soil moves away, gets um, flows away due to saturation or some other condition, creates a void, your house can sink. Not a desirable thing to happen. Another professional tool that's come in recently, within the last, 20 years? I'm not sure exactly, is Google Earth. Google Earth is a wonderful pre-investigation tool. Somebody hands you a project on a piece of property. One of the first things you want to do is go to Google Earth and look at that property and see if you can get some feel for what type of ground it's on, what the features look like from up above, where existing structures are, all sorts of things. You can get quite a bit of information, perhaps steepness of slope and other information that are valuable to help you plan your investigation. Here's another tool which is very useful. This is the National Geologic Map Database. It's really good for an online method of finding out what formations may underlie your project. So you just go to Map View down here, and that'll bring you to a drop-down menu. You type in the address of the project, street address. It's pretty precise, and it gives you a locator or a location, and you can see from the geologic mapping that's compiled on this database what the formation is underneath your proposed project. In the city of San Diego, we have a series or a set of maps prepared by the city, which are collectively known as the seismic safety study maps. This is the San Diego area arranged into a grid of map tiles, they're called, and each one of these tiles gives you geologic information. The orange areas labeled as number 21 mean landslide prone areas. The pink areas, the red lines you see here, some of them are dashed, some of them are solid, are actual mapped faults. So this is the Rose Canyon fault zone, which is an active fault zone in San Diego. Here's an offshoot from the Rose Canyon fault system, the Country Club fault. There are other designations here, more landslide areas up here and up here. These are stable, fairly level, flat terrace areas. So you can see this is a pretty good planning tool. Let's say you have a project, somebody wants to build a nice big house right here. Okay, so because you're close or within a designated fault zone area, you're going to have to hire an engineering geologist to go out, trench across your property to see if indeed any active or potentially active fault crosses your property. If so, if it's an active fault, you may have to set back your structure 25, 50 feet away from that fault. You're going to have to do something in consideration of the presence of that fault. Some of you may be able to cross your eyes or let your eyes drift apart to lock in the three-dimensional aspect of this stereophoto pair. Aerial photo stereo pairs are very, very useful tools to look at dimensions and features of an area, geologically speaking, in 3 dimensions. The county of San Diego used to have a huge collection of aerial stereo photos, which were really useful in getting more geologic information. When I worked for the Forest Service, they had thousands of stereo pairs, and those were very helpful, especially in forested areas, to look at slope steepness, stream banks, cut areas, areas that were devastated by fire, areas where roads had penetrated into the timber sales area, for example. They're just a really good tool. They give you a pretty accurate, although slightly vertically exaggerated picture three-dimensionally of features on the ground. And if you can find them for your project, use them by all means. They're not always easy to find, and sometimes not available for certain areas. Anyway, that's a generalized look at how you approach a site assessment, geologically speaking. You have to get your act together, use tools to assess whatever is known about the property before you investigate it, and then you have to go out and assess ground conditions, whether they're bedrock, soil, clay, etc. So an engineering geologist should be locked into all that kind of stuff so that you can go out and drill or dig or whatever you need to do to look at the subsurface, to get samples, put all that stuff together, put it in a report, work with engineers and architects to develop a good, viable project. Thank you.